Hey, hello, welcome back. Today we're gonna have a lecture on an algorithm called latent discriminant analysis, also known as LDA. I'm Professor Wu, so let's get started. In order for you to understand LDA, there's a lot of math involved. So, as always, it's nice to basically review some of these core math. And one of them is called a batch projection. We've done batch projection in the previous lecture on PCA. So basically, if we have multiple points, and we want to project them onto a single line, right? So the way we would do it is if we have the multiple points aligned inside a matrix, so a single projection is simply X transpose V hat, right? Now, if we have multiple of them, we can simply stack the X transpose X1, X2, X3 into a matrix. And when we multiply V hat by the X, we get the alpha values, which tells us the distance, right? Tells us the distance to each one of these points. And that's the new coordinate. So this is like, in a way, the batch projection. Now, this is great because it tells us the distance from zero to each projected point, right? Zero to each projected point. However, what if we want the actual points themselves? Instead of the distance, we want the actual points right here, right here, right here, and right here. Well, all we have to do is multiply the vector. All we have to do is multiply the vector v hat, this is v hat, by each one of these. Okay, so if we multiply by v hat transpose by this, then we're going to get all the vectors. You can kind of picture if v is like 1, 0, right, and the distance is 1, 2, 1, 4, then it will be, this is equivalent to 1, 0, right? 1 multiplied by the direction, 2, 0, 2 multiplied by this, 1, 0, 4, 0. Notice how when we multiply the vectors alpha by v hat transpose, we automatically multiply v hat with all of them simultaneously. Therefore, you can get the equation. We know how to get alpha, so this is alpha, and then multiplied by v hat transpose. So this allows us to essentially get all the points, all the actual points along the projection. Okay, so this is essentially how you can do batch projection and get all the points. Now, in order for you to really consolidate this idea, you need to perform this. Take this data. Here's the data, right? And what I want you to do is project it onto the vector v. This is the vector v. This is not normalized. So perform this batch projection, and basically what you want to do is perform the batch projection and plot this out. Make sure you're able to essentially get all these points. Okay, so that's your first exercise. Pause the video and actually try to do it. All right, I provide a solution here, so hopefully you are able to do it. All right, so after you understand batch projection, the next concept I want to cover is called the covariance matrix. We've previously learned about covariance, right? So covariance give you the dependency between x and y. So what is a covariance matrix? Well, covariance matrix, it's simply if you have two variables, covariance matrix, as you've seen, it will be covariance x, covariance of x, y, covariance of y, x, covariance of y, y. It's basically every single combination. So that's what a covariance matrix is, right? So, okay, a quick review. Remember what variance was? And we, from the last class, learned that the variance is simply x transpose cx. Right, this is from the PCA conclusion. And over here, we learned that the covariance is simply 1 over n x transpose cy. Right, so these are the equations for variance and covariance. Okay, so covariance matrix is the combination of covariance and variance. And it's, even though we've only seen it with covariance of x and y, we can have more than 2 dimensions, right? So let's say we have 3 dimensions. So we're trying to find the dependency between the 3 of them. How do we go about defining this dependency? Well, let's say that x1, x2, x3, we're trying to find the dependency between the 3 of them. What we can do is we can simply put them into a matrix. So that's the first column, second column, third column. And then we simply, when we are trying to find the covariance matrix, what we do is we construct this matrix as such. You have covariance of x11, 12, 13. So it's basically you're finding the covariance between every combination. 21, 22, 23. 31, 32, 33. Okay? So the covariance matrix is essentially just every combination if you have 3. Of course, if you have 4 variables you're trying to measure the dependency, then this will be a 4 by 4 matrix. Now, for the diagonal, we know that x1 is just the variance of x1. The second one is variance of x2, and the third one variance of x3. Okay. Now, when you're computing the covariance matrix, the easy way is you can just do them one at a time, right? You can calculate. So you have to calculate 9 things in this matrix. Of course, you could do that, but that's a bad idea. That's a bad idea because it takes forever. You have to calculate a lot, like 9 of them. It turns out that there's a very simple way to calculate this matrix. And this matrix, to calculate it, it's simply 1 over n x, the data matrix x, center x. Like this is a much faster way than if you try to calculate each one of these terms individually. Okay, so this is what you want to do. Where C is the center matrix and X is the data matrix, right? So if you have 3 dimensions, in this case, the first dimension data will be x1, second dimension x2, third dimension x3, so on and so forth. You can have more dimensions. So here's the question. Calculating this seems really complicated. Calculating this is like much easier. Are they really mathematically equivalent? Right? They are mathematically equivalent, but how do we know that? Well, you're going to prove it right now. Right now, let's assume we're just doing 3 dimension, right? Therefore, the data matrix is x1, x2, x3 as the columns. To remind you, this is the definition for variance for the first dimension, variance for the second dimension, variance for the third dimension. And the covariance between 2 follows this equation. What I want you to do now is to pause the video and essentially see if you're able to show that the covariance matrix is equivalent to this. Now, give it a good honest effort of 5 minutes. If you still have no idea how to do it in 5 minutes, you can go ahead and look at the solution. But try to see if you can get whether they're the same or not. Okay, pause the video. I'm going to go on now. All right, so the solution. Well, as I told you, the covariance matrix is simply the covariance of every single combination of dependency. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, right? So now all we have to do is write the actual definition of the covariance for every single one of them. Now, what is interesting is that if I define x hat 1 as these terms, so this is a vector. This is a vector of these terms. X hat 2 as for the second one, x hat 3 for the third one. Then the covariance matrix, notice how it's simple, can be simplified into these terms in terms of x hat 1, right? Notice how this is x1. If you take this multiply by itself, it's equivalent to this term here. So this right here can be simplified. And now we can further simplify this. This right here is really the multiplication of x1 and this one. Right? Notice how this right here, this goes here, this goes here, this goes here. All right, take a second, see if you can get that these two are equivalent. Well, once you see that these two are equivalent, then then let's take a very close look at this. What is this? Well, if I fill it in with these three vectors, then it's going to look like this, right? Three vectors. And now we can split these into one single matrix, which this is just the original matrix. And this is the average repeated multiple times. So if you have the matrix minus the mean, which is equivalent to matrix times the centering matrix. That's how it comes about. So what it's saying is that this part is the centering matrix. This is the transpose of the matrix center. And therefore, when we multiply them together, we get this result back. You have seen this many times. This occurred in PCA, right? This has occurred. So when we were solving PCA, like what we were doing is we essentially obtained this Q matrix, and we're trying to basically find the V that maximizes. So this Q matrix is actually the covariance matrix. This is why we call this the covariance matrix. And the covariance matrix, now you understand what it is. It summarizes the dependency and variation between multiple variables. If you have 2, 3, 4, then it the matrix summarizes all of them. Now, if we then have the V multiplied by Q, remember in PCA, that is the variance after we project the data. So this is a matrix. This is a number, right? After you project it, then you get the variation number. So this is the variance. And this is a matrix. This is a covariance matrix. So you want to keep these two concepts straight in your head. In PCA, what we're trying to do is we're trying to maximize the variance after projection. So we take the covariance, we project it onto V, and we're trying to maximize the variation. Okay, so I think we've covered enough math now. If like hopefully you're convinced that this is the covariance matrix. I think we're now ready to basically move on to LDA, which is today's algorithm. Remember what PCA does. What PCA does is it's trying to find a line, a vector, which after you do the projection, the result looks very similar to the original data, right? This would be an example of a projection that the final result doesn't look like the original data, okay? So, and as a result, in PCA, we're trying to find a line projection such that the variation after the projection, the variance of the after projection is maximized. Okay, so that was what PCA does. Now, the downside of PCA is that, well, the upside of PCA is that it maintains the original shape. However, that's also the downside. Sometimes we may not want to maintain the original shape. In this particular case, notice that we have the data. And if you want to maintain the original shape, you would perform PCA and you would look like this. However, notice that now you have basically the data that's all mixed together, right? Therefore, if you have an end goal where you're trying to separate the green and the orange dots, you just made it harder. Like previously, it was easy to separate them, the green and the orange, but now you have them all mixed together, and it makes it much harder. So, in cases where you know the label, you know these are green, these are orange, and you're trying to keep them separated, PCA may not be the best way to reduce the dimension. Like you might want to use some guided method of using the label to guide you so that you maintain the integrity of the separation. So if you use PCA, you will look like this. The idea of LDA is that you project it onto a line such that it maintains the integrity of the cluster groups. So orange still stay within orange, green stay with green. Whereas over here, you no longer maintain the integrity of the group. Okay, so that's what LDA does. So PCA doesn't have no labels, right? It just reduces the dimension. LDA, you have to have labels because you're using the labels to guide you to perform a projection. Okay, so that's the difference. All right, and this is LDA is the linear discriminant analysis. So LDA is an algorithm that lowers the dimension of data with the guide of labels. Okay, that's what I just said. And the idea is you want to find a projection. You want to find a projection such that the two clusters, you have two clusters, you want the center of the two clusters to be as far away from each other as possible, right? You're pushing the two clusters away. That's how you can tell them apart. The farther apart they are, the better. So you're trying to maximize the distance between the centers, center 0, center 1, right? You're trying to maximize their distance from each other. And you want the clusters to be as small as possible. You can imagine if you don't make the cluster small, maybe one cluster is here, one cluster is here. So you have an area of ambiguity where they're mixed together. And mixing two classes together makes it harder to separate them. So we want to avoid them. Therefore, if we can push the center apart, so the center is still the same, but we make the cluster as small as possible, then it's easy to tell them apart. Whereas this, you have an area of ambiguity and it's difficult to tell them apart. So it has two. So it's trying to minimize the variation of cluster 1 and variation of cluster 2, right? Well, cluster 0 and cluster 1. Cluster 0, cluster 1. So it's trying to maximize the distance between the center while minimize the variations of the cluster. So that is the goal. If we can mathematically define the center and the variation, the problem is solved. And what we do, and as a result, it turns out that the objective of LDA looks identical to PCA. So this is what we did in PCA, right? The only difference is that in LDA, the Q matrix is defined differently. So if you know how to solve PCA, you know how to solve LDA. The only thing you need to know is that Q is defined by this two, the product of these two matrices, S1 and S2. So what S1 does is basically S1 separates this matrix contains the information of how you can separate the data, the center of two clusters. And this S2 contains the variation information where you're trying to minimize. Okay, so so that's it. That's it. The objective is the same. Where in PCA your Q is equal to this. In LDA your Q is equal to something else. Okay, so PC and LDA, like basically same objective, just different Qs, just different Qs. So our goal today is now figure out where did this equation come from. Okay. Now, first step, like I said, we're trying to push samples of different classes apart, right? Ideally, we want the two data sets after projection to be as far apart from each other as possible, because the farther apart they are, the easier we can tell them apart. So having them far apart is great. Now, how do we do that? Well, we can define the center of cluster 1, no, cluster 0. We're going to call it, this is cluster 0. So we're going to loop through all the points in cluster 0, right? And then we do the projection. After the projection, we find the average point, and that's the center. So that's the center after projection. So you have all these dots. After projection, the center of the projection will be right here, right? So that's after projection. Now we do the same thing for cluster 1 as well. So cluster 0, cluster 1. For the other cluster, what we do is we do the projection, and then we find the average point. So we find the average point. So we know the center, the average, the center for the cluster 0 and cluster 1, and we want the distance between them to be maximized. So we want to find the vector projection such that the distance of the center is maximized to be as far apart as possible. And this becomes our first objective. This is what we're trying to do. Now, this right here, as your next exercise, our goal is to take this, and we know the definition is C0 and C1, right? We want to take this and we want to write this into the final form. The final form is that we want to multiply this out, and you'll give us something that looks like this, where we result in an S1. Okay, take a moment, see if you can go from here to here. okay, by plugging these in and multiplying it out, okay? And try to identify what the S1 matrix is, okay? Pause the video. I'm going to go on. Okay, so this right here, like I said, we know the definition, so we can just plug C0, C1 in. And when we have a square with L2 norm, it's equivalent to, if you have like a number V, L2 norm, this is V transpose V, okay? So this is what that means when you have an L2 norm. And then what happens is you take this times itself. So you take this transpose times itself. When you do that, the V pulls out on both sides. And notice how this right here is simply this average point. This is the average point for group 0, and this is the average point for group 1. I'm going to call the average point for group 0 as the bar average minus the average point for group 1. And this is just the transpose of the same thing. So this right here, we're going to call it matrix S1. So this right here is S1. So this is how we end up getting this expression. If we were to find a vector such that this expression is maximized, we will essentially find a projection such that the center of two clusters as pushed as far apart from each other as possible. Okay? That's how this works. All right, so for your next practice, I want you to create the S1 matrix. Now remember how to create the S1 matrix is the average point from group 1 minus the average point from group 2. Then you will essentially get this, okay? So practice creating the S1 matrix and then actually perform the projection. You should, after you do the projection, you should see something that looks like this, okay? So try to produce this plot, basically, okay? I have the solution here. Pause the video, go ahead. All right, next. Now, we have performed the first objective. The first objective is after you perform projection, ideally you want to maximize the distance between the two centers. However, there's a second objective. The clusters may be too big after you do the projection, right? So that the clusters could overlap each other in certain areas. So ideally, we want to push the centers apart, but simultaneously, we want the clusters to be as small as possible. So that's the second objective. Well, that's easy because if we're trying to make the clusters as small as possible, essentially for cluster 0, the data is within cluster 0, we want to minimize the variance, right? This is the opposite. So this is the PCA objective, right? But in PCA, we're trying to find a vector that maximizes the variance. But in LDA, we're trying to make the variance as small as possible because we want them tight. So we're trying to minimize this. So now we're trying to minimize for the cluster 0, and we're trying to minimize for cluster 1. So we can combine these two objectives, cluster 0, cluster 1, which we can pull the terms out, resulting in this. Okay, so we're going to call this S2. So now, if we find a vector that minimizes this, we will essentially find a vector that makes these clusters as small as possible. Okay, so we have now one for S1, right? We're trying to maximize the distance between centers, and then 2 for S2, we're trying to minimize the cluster size. Well, there are different ways to combine these two objectives. One is you're trying to maximize this, right, and minimize this. So you just do the inverse of this. So you notice how you're trying to maximize S1, and you're trying to maximize the inverse of S2. So that's one way to do it. This is called a Rayleigh quotient. Another way to do it is if you simply multiply S1 by the inverse. So you're trying to maximize S1 and then maximize the inverse of S1. So that becomes our Q matrix, right? And the third way is you can just add S1 and minus S2. So you're trying to maximize S1 and maximize the negative of S2. So there are three ways to do this, but for this lecture, we're just going to focus on this approach. Okay, this approach. I think this is the original approach, but this is, in my opinion, the easier approach to do. So you just you know S1, you know S2, you know Q, and therefore we now simply solve the identical objective as PCA. So now you know how to solve this with PCA. It's just the eigenvectors, and that's it. That is how LDA works. You will find a vector for projection such that you will essentially maintain the cluster structure while pushing the centers as far apart from each other as possible. Okay, I think that's it for today. So for you to practice, these are the two clusters. What I want you to do is essentially perform PCA and LDA. So this is the result from LDA. This is the result for PCA. So I want you to follow the instruction and reproduce these plots. Okay. So this is, yeah, you can see how you're able to keep them separated, whereas PCA mixed all the data together. Okay. I have the solutions here. You want to make sure you look through them. And that's it. I will see you in the next lecture.